Hi everyone. So today I'm going to be talking about an irrational slope Thompson Group variant and its BNSR invariant. So I'm sure many people watching are familiar with Thompson's group F. This is the group of piecewise linear orientation preserving homeomorphisms of the unit interval where the slopes for all paths are 2 and the breakpoints land on dyadic rationals. So this group is F infinity, as was proven in the 1980s. Obviously then has a finite presentation, but it's more common to use the infinite presentation shown on the screen. And you may also know that you can represent Thompson's group using tree pair diagrams, such as the one in the bottom right corner here. So the variant we're going to talk about is very similar in structure, but instead of the slopes and breakpoints being based around 2.5, they're going to be based around this irrational number tau, which is the small golden ratio, or the solution to tau squared plus tau equals 1. So what this means is when we break the interval in Thompson's group, we normally do it by breaking it into 2 equal pieces, but here we're going to break it into a piece of length tau and a piece of length tau squared. So this is going to introduce asymmetry in a way that isn't apparent in Thompson's group or the more general Brown-Thompson groups, because normally you're breaking the interval into equal pieces. Here, because they're unequal, it's possible for them to be either big side left, small side right, or big side right, small side left. So you can see that this is going to create 2 different caret types in our tree pair diagrams. Tree pair diagrams are still possible, but you need to adapt because of that. So recently, as recently as last year, we have a presentation for this group. But when this group was first written about by Cleary in 2000, he was able to show it was F infinity. He just didn't have a presentation at the time. So we're going to talk about the BNSR invariant for this group. So quick primer for BNSR invariants, or at least how they're defined. They are a subset of the character space for a group. So if we have a character space, a set of homomorphisms from the group to the real numbers, we're going to introduce an equivalence relation on that by saying that 2 characters are equivalent if you can multiply one of them by a real number to get to the other one, which just means that anything on a radial line out from the origin is the same under this equivalence class. So equivalence classes are therefore going to be a circle of equivalence classes around the origin. So this is going to be what we call a character sphere, and we're going to start with that as our base for the BNSR invariant, and then we're going to calculate whether one of these equivalence classes is in the BNSR invariant by taking the Cayley graph of our group and labeling each vertex according to what value the group element represented by that vertex is assigned by our character. So if chi of g is equal to 2, then that vertex is going to be labeled 2. And then we're going to cut our Cayley graph in half and take all the vertices that have a label greater than or equal to 0. And from there, we're just going to see if that top half of our Cayley graph is connected. If it is connected, then that character is in our BNSR invariant, otherwise it's not. So that's how we define the first BNSR invariant, and we can generalize this in to a BNSR invariant for every natural number by requiring our group to be Fn. Normally we require it to be finitely generated, but in this case we need it to be Fn for the nth sigma invariant. Instead of a Cayley graph, we're going to use a model for EG, and if any model for EG works in this case, then it's fine. You just need one of them to work. And then once we've cut that EG in half in the same way that we cut the Cayley graph in half, we're going to require it to be n-1 connected. So it needs to be 1 connected, so it needs to have no non-trivial loops for the second sigma invariant, and so on and so forth. There's obviously some nuance there that I'm kind of skipping over, but that's the general idea. So looking at F, when the sigma invariant for F was calculated by Beery, Gauguin, and Koshlikova in 2008, they relied on a few key facts. So they had F is isomorphic to its own subgroup F1, where you just cut off the first generator, and it's the subgroup generated by the rest of the generators missing the first one. And therefore that subgroup is F infinite. And then they were able to write F as an ascending H and N extension of that subgroup. So if we try and like directly transfer these properties over and see if they hold in F tau, the first one does. The F tau is isomorphic to its subgroup with missing the first generator, and it's F infinite, so the subgroup is also F infinite. However, the ascending H and N extension of that subgroup is not F tau. Instead, it is an index 2 subgroup we call K, where it is missing one of the generators that F tau requires. So what we needed then was a way to link the sigma invariant of this subgroup K to the sigma invariant of F tau, because this process that Birgogan Koshlikova allows us to calculate the sigma invariant for K, but not for F tau, because K is the result of the ascending H&N extension, not F tau. So what me and my colleague Yuri Santos Rigo were able to do was to show that if a finite index subgroup has the same abelianization as its parent group, then their sigma invariants have to be the same. And so there's a few reasons for that, which I'm going to kind of skip over for time purposes, but it's generally the case that when a subgroup is finite index, it's going to have, and the abelianization is the same, it's going to have the same characters. So all of the character space is going to be the same. And at the same time, a model for EG if G is the parent group is necessarily a model for EH as long as H is finite index in that group. So we have the same we have the same space and we have the same characters, which means that any way we calculate the sigma invariant, it's going to end up the same. So because of this, and because we know that the abelianization for this subgroup K and the abelianization for F tau are the same, we know their sigma invariants are going to be the same. So we just need to calculate for K and transfer up to F tau, which is exactly what we did. And so the final result is very similar in form to the sigma invariant for F, if you're familiar with that, which is that the character sphere is the one sphere, the circle, embedded in R2. The first sigma invariant is just missing 2 points, the character that calculates the right slope at 0 and the character that calculates the left slope at 1. And then every other sigma invariant from 2 to infinity is missing any character that can be made as a positive linear combination of those two characters. And that's the sigma invariant for F tau as it stands. Thank you for